Oh, hi Kat. It's so great to talk to you. This is Dr. Entropia, broadcasting from the tree lab, and welcome to today's interview. So before we get to tree lab on the top floor, you need to gain access to 2 other floors, one by one, by problem solving. But no worry, just take it as a game in which you are now at the ground level. There are 2 other lower levels. One is the micrometer floor, where everything is in the scale of a few to hundreds of micrometers, about the size of a cell. The other is the nanometer floor, where everything is measured by tens of nanometers in length, about the size of a protein. In every floor, you will be given some stories about a molecule named Auxin, as well as some related questions. If you get all the answers right, voila, you'll be officially one of us. Speaking of the discovery of Auxin, where shall we begin? Well, let's go back to some 140 years ago, the year 8080. It began with a scientist named Darwin. Yes, my dear, that Darwin, the one who created the biological theory of evolution, who is also interested in experiments using plants and lights. The subject that he used was a very special newborn part of a plant. It existed before the first leaf showed up and acted like a protective sheath around the stem. We've got a scientific name for it, coleoptile. What Darwin did was to expose the coleoptile to light coming from one specific direction, which is called unidirectional light. And he found the coleoptile was sensitive and responsible to light. And which part was responsible for that? To answer it, he either covered the tip or body part of the plant. When treated with unidirectional light, only the one with the body cover bent. The tip covered one lost its sensitivity to light. Same thing happened when he removed the tip and exposed to the light. No curvature, no bending in both cases, with the tip being covered or removed. Therefore, he came to the conclusion that the tip was the light-sensitive part, and something produced in the tip regulated growth, elongated the coleoptile, and induced curvature. As a scientist, we've always wanted to know more, so we ask ourselves, how does it work? Does it stay in the tip, or being transferred downward to carry out its function? To answer that question, Danish scientist Boyce and Jason designed several sets of experiments in 1913. He cut the tip off and placed a thin piece of mineral called mica and put it back. This mica piece acted like a barrier, preventing the chemicals in the tip from moving downward. It turned out the coleoptile didn't curve toward light. Then he made a slight change. He cut the tip and inserted a piece of agar this time. Unlike the previous mineral piece, the gel-like agar was something that allowed the chemicals to pass through. This time, the coleoptile did bend toward the light. The 2 experiments help explain the way the magic substance worked. Rather than stay in the tip, it was transferred downward to elongate the lower part to cause the bending. Boyce and Jason didn't stop at this stage. Instead, he went further to investigate the details of how it was transferred. Next, he inserted a mica piece under the tip, not fully under, only part way into the side. He noticed the way the mica piece was placed affected the result. If mica was put bright side, coleoptiles continued to bend. However, when put in the dark side, the plant lost its light sensitivity. That means if the chemical had to go down to have its effect, it must be transmitted through the dark side to promote more growth along this side. Now that we know this is a chemical, or in another word, hormone, we'd like to capture the hormone, make it work under our control. In 1926, a graduate student from Holland by the name of Fries Wen came up with an idea. He cut the tip and placed it on an agar block. The hormone would be diffused and trapped in the agar block. Then he removed the tip, placed the agar full of magic hormone on top of other coleoptiles, of which their tips had already been cut. Just like before, the way the egg was placed mattered. When put in the center, it grew straight up. Only when the egg was put off-center would curvature occur. No matter which side the egg stayed, the curvature occurred away from that side, as if it was growing toward unidirectional light. That's to say, bending caused by exposure to unidirectional light can be replaced by getting hormone in the egg. Same thing happened even when the plants were grown in the dark. Now the bending could be controlled as scientists well. Therefore, when proposed, this was a growth-promoting plant hormone, and he gave it the beautiful name Auxin. That's a pretty long history, isn't it? But our story hasn't finished because there's one last self-designed experiment awaits us. Consider a coleopter, with the tip being carved and placed to the left side of another carved surface. When kept in the dark, which of the following will happen? Will it stay erect, bend to the right, or to the left? Terrific! You nailed it! It does bend to the right because the oxygen molecule in the tip will be transferred downward in the left side, promoting growth along the left side and cause it to bend toward the other side. Now the next micrometer floor is unlocked. Go ahead and the new adventure is awaiting you.